Okay, all right, so let's talk about support vector machine. This is a very old topic, but it is so useful that even nowadays people are still using support vector machines. And therefore, as a introductory machine learning course, we have to talk about that because it is just so powerful. Support vector machine, it is one of the discriminant methods, and it sort of comes out from the perceptron algorithm, where if you remember, when we talk about perceptron algorithm, we define the notion of gap from a point to a plane. That defines something called the margin. And there are questions saying that, all right, if you have perceptron algorithm, you find a decision boundary which is so close to your one of the two data points on the two sides. Isn't it very sensitive to perturbation? The answer is yes. Perceptron is non-unique and is very sensitive. And there are also questions, very excellent questions, asking, what if I find a unique solution that is right in the middle of the two data sets? Isn't it the best? It is indeed the best, but to find that solution, you need to solve the support vector machine problem. And the support vector machine solution is exactly the thing that you're thinking about. Okay? And so there will be 3 lectures on support vector machine. This is the first lecture. I'm going to introduce a concept called the max margin. It is an optimization problem. I want to formulate this problem, and then I want to show you what is the visualization of this problem. I am not going to show you how to solve this problem, okay, because solving this problem will require some work. I will only tell you the program. I will tell you how to type these equations in CVX. That will take you only a few lines. It's fairly straightforward. If you have a Python library, you can even strictly just call SVM. There are built-in libraries to do the SVM. So we won't talk about the optimization perspective too much as of today. We'll do more next time when we talk about the duality, because the duality is really the powerful aspect about SVM. And then the third lecture on SVM will be focusing on kernel SVM, something that allows you to handle the nonlinearity. So by now, it is already the 3rd time that we're seeing kernel methods. Okay? And so I hope that this kernel SVM will appear a little bit more natural to you guys than it was the first time. Okay, so this lecture will talk about the concept of margin and then the support vector machine optimization. The concept of margin comes from here. If you have 2 data sets, you have a data set that contains 2 classes, you can always draw a band where within this band, you may or may not have data points. Okay, so you can have 2 classes of data points. Okay, so if you draw the decision boundary, you will be able to see the band. Now, this is a linearly separable case. Okay, linearly separable, and therefore I'm always able to find a band where within this band there is nothing there. And this band is defining what we call the margin. Now, of course, if you look at this case, this is a very narrow margin. For the same set of data points, if I draw the decision boundary as follows, I will have a bigger margin. Now, which one do you prefer? Well, of course, you would say this is a bigger margin, and so it's more tolerable to any perturbation. And by perturbation, I mean that if you move this data point a little bit left or right, you will not make mistake. Compared to this data point, if you just move left or right a little bit, you are likely to make a mistake. Okay? So you will prefer to have a max margin classifier. Now, we are going to talk about the generalization later, but bear in mind that a max margin classifier is not necessarily the Bayesian optimum classifier. The Bayesian optimum classifier says that I'm going to minimize the probability of error. This one says that I'm going to maximize the margin. These are 2 different objectives. Okay? I'm going to show you cases where the support vector machine solution is not the same as the Bayesian oracle. Okay? So just bear in mind that the 2 are different. And you ask which one is better? Well, that really depends on what is your objective. If your objective is to have the most robust classifier, then this will be the solution. If your objective is to get the best classifier in terms of performance, you don't care about robustness, then the Bayesian will be the best according to that metric. So it really depends on what metric that you're using to say which one is better. You will have a different choice. So we are going to look at this max margin classifier. And then the questions, of course, that we need to ask will be, since it is a measure of the margin, I, of course, need to calculate the distance between a point and a plane. Second, how do I formulate this optimization problem? And third, how am I going to solve this optimization problem? So this will be a very logical sequence of problems that we need to ask. So here is a review of what we have done when we first talk about classifiers. It is the problem of how do you find the distance between a point and a plane. Let me remind you, this is the discriminant function. This is called the separating hyperplane. The hyperplane will be is a set that contains all the x such that this line will equal to 0. Okay, and then this vector w divided by the 2 norm of w is called the normal vector of the separating hyperplane. And so, if you want to calculate the distance from a point x0 to this plane, you need to do what? Well, you need to first look at this normal vector, which is pointing from the plane to the point. And any travel from this plane to the point has to go along with this direction. Otherwise, you won't have the shortest distance. And so you say that this x0 has to be xp. xp is a point on your plane plus some kind of a search direction along the w. And then eta will be a step size. Okay, xp is something that you want to find out. And therefore, going through all these derivations, you can show that if I pick xp as my point and put it into g, and since xp is living on my plane, it has to give me 0. And therefore, I can write this g of x0 as this, and then x0, according to this definition here, I have this xp. And since g of xp is 0, I can simplify this g of x0 in terms of eta times w2 norm. That should be the second time you're seeing this. Okay, so it shouldn't be too surprising. Once you get to this point, then you can show that the distance between this point x0 and then the point on the plane xp is given by this ratio of g at x0 divided by the 2 norm of w. That's just a straightforward calculation from the previous slide. And therefore, you know that the closest point, xp, will be given by x0 minus gx0 divided by w2 norm, and then that will be the search vector. And so the conclusion is what? Well, the conclusion is that this xp can be written as x0 minus a distance times the search direction, which is the normal vector. And so this would define the distance. And if you have two data points here, two classes of data points, you can define the margin by just checking which one will give you the smallest distance. Okay, so that will be the direction that we're going towards. Okay, all right. So given all these results, we can try to define a term called the unsigned distance between a separating hyperplane and a data point. How do we define that? I just tell you that the distance between a point and a plane is given by this ratio. You put the data point into your discriminant function divided by the 2 norm of your w. That will be the distance. So if I have a data point xj, let's say I'm looking at this guy, then I just need to put xj into this equation and evaluate. That will give me the distance. I repeat the same exercise for this data point, for that data point, for this data point. Then for every data point, I will be able to calculate the distance between the point and the plane. That will give me this d of xj, where j is the jth data point, and h is my separating hyperplane. I can calculate this distance for every single data point in this data set. And look at this. This is an absolute value of the discriminant function, and therefore is always positive, and therefore is called the unsigned distance. It's literally measure the distance between the point and the plane. Okay? There's no sign. There's no plus, there's no minus. is just the absolute distance between the point and the plane. Okay? So you ask, what happens if I have a red dot going to here, going to the other side? You still can calculate the distance because it is unsigned. Okay? All right, so now let's move on. What is the margin? The margin is the smallest distance among all the possible distances in a data set. So what I mean is that you first calculate the d of xj and h for every single xj, and then you have a collection of all these distance, which is the distance between plane and point, and then among all these distance, you pick the one, and that gives you the smallest distance, and that will define a thing called the margin. Now, of course, if you change the separating hyperplane, you move it, you tilt it, you orient it, you change it, okay? Then your margin would be different. And therefore, this margin, this gamma, this number is a function depending on the W and also the W0, right? Because this H is defined by W transpose X plus W0. So if you change W, you change W0, this gamma will change. Okay? So the gamma defines the margin, and what do you want? Well, of course, very soon we are going to maximize this gamma, subject to certain constraint, right? Because by maximizing this margin, I will be able to give you the biggest band, and you will be happy. Okay, so that will be something that we want. Okay, so just a few comments here. This gamma, this margin, depends on W and W0. And if you have a finite set of data points, and this mean operation is well defined. Okay, and that also works when the red point is on the other side of the separating hyperplane because it's unsigned that you can always calculate that number. Gamma is always positive because it's unsigned. Now, we are going to do something interesting, which we want to characterize when a data point is misclassified. And to do that, we want to go away from the unsigned distance to a thing called the signed distance. Now, how do we do that? We're going to assume that you have a set of labels, and the labels, they are either +1 or -1. And then I'm going to define my signed distance as y times the thing that I had before. Okay, so this is just, this quantity here is just a g of xj divided by the 2 norm of w. Okay, so this is the unsigned distance. And then here you will have the yj coming out. Okay, now this is not exactly unsigned distance because you don't have the absolute sign, but that would be the quantity that you use to calculate the unsigned distance. This will be a signed distance. Now, you look at this pair of numbers. If your xj is on the positive side, and then your label is also positive, then you are correctly classified, and therefore your distance, your signed distance will be positive. If you have a mismatch, then you will have a negative value. Okay? This is exactly the same as when we define the perceptual loss function. Remember that? This is the discriminant function that will give you some number. If they match this, they are both on the positive side, you get positive value. Okay? Alright, so this signed distance will not only tell you the distance, it also tells you whether your data point has been classified correctly or wrong. And so here is the picture. You have two classes of data points. In this example, the blue and the red data points, they are correctly classified. And so all the distance, the signed distance, they are positive. Here you have one point, xj, that is located on the wrong side of the separating hyperplane. And therefore, if you calculate the signed distance of this xj compared to the separating hyperplane, you will get negative number. Of course, if you just calculate the unsigned distance, that will still be a positive number. However, since this data point is misclassified, you get negative value. Okay, so what is the max margin problem? So let's make an assumption here that your data set is linearly separable. Now, if it is linearly not separable, we will deal with that later. There is a thing called the soft SVM. Right now, we're talking about a thing called the hard SVM. So let's assume that the data set is linearly separable. What it means is that when you take the signed distance, okay, you have a label multiplied with this discriminant function. It has to be bigger than or equals to gamma for some gamma. Okay, for every data point, because you can correctly classify it, right? So you have two classes of data points. No matter how you draw your decision boundary, if you want to get a correct decision boundary, you at least should have some positive gamma. Because if you draw the decision boundary here, this is a not allowed decision boundary. Because your data set itself is linearly separable, that means you will be able to find a separating hyperplane that's sitting somewhere in the middle. That will be able to give you a positive gamma, right? And so this criteria has to be satisfied for all the data points if it is linearly separable. Okay, so if this holds, then all the training samples are correctly classified. That means you will be able to find a separating hyperplane. And then the training samples will have at least the distance of gamma distance from the boundary. Okay, because everyone has to be bigger than gamma, and so you should be able to come up with the smallest gamma that is positive. So what is the problem? Well, the problem is the following. It should be easy to understand now. You want to maximize your margin, okay, by moving your plane left and right, up and down, okay, because if you don't find the right separating hyperplane, this gamma may not be maximized. So you want to maximize your margin. However, you also want to ensure that all the data points, they are correctly classified. Because if you do not have this constraint, well, I can just maximize the margin, but by maximizing the margin, it may not be guaranteed to make sure that all the data points are correctly classified. Okay? So this constraint optimization problem is the support vector machine problem. Okay? If you solve this problem, you will get the support vector machine solution. Okay? That will be the max margin solution. That would be the most robust solution as far as the linear classifiers are concerned. So let me draw you a few pictures to make sure that you understand what I mean by max margin solution. This is a max margin solution. I put a checkpoint here. Why? You look at these two data sets, okay? So your two classes of data points. This margin is maximized. In addition, all the data points, they are correctly classified. Now, let's look at another case. In this case, the two data sets, they are still correctly classified. However, this separating hyperplane does not yield you a maximum margin. Now, you can compare to the previous plot. These data points are exactly the same data points. What I'm doing, I'm just moving my separating hyperplane around, turning the angles around. Okay, so if I turn the angles to here, then you see that the margins are not maximized, and therefore this cannot be the solution of your support vector machine problem. Now, how about the constraint? What will happen if I violate the constraint? This is an example. Your margin is somewhat big, okay? However, in this case, one data point is sitting on the other side. Then this is not a support vector machine solution because your constraint set is violated. So in order to get to the support vector machine solution, you really need to achieve two things. One, the data points that are correctly classified. And two, this margin has to be maximized. Is that all right? Is that intuition clear? This is how people define support vector machine. Now, the following discussions will be a little bit more mathematical because to solve the problem, by solving the problem, I mean that to solve this problem is non-trivial. Why? Well, because you want to maximize over W and W0. and W0 appears in the numerator, it appears in the denominator, it also appears in gamma, because if you change the W, the gamma will change. Okay? And therefore, it is very unclear how you're going to solve this optimization. You cannot just type this equation into CVX, and CVX will complain because it cannot recognize the format of this problem. So what we are going to do in the following 20 minutes is to turn this problem into a quadratic minimization problem that the CVX can recognize. And after turning into that format, you will recognize a thing that is very common in all the textbooks. Okay? Now, if you only look at this formulation, it may not be that obvious. If you go online, you type support vector machine, it will not pop up this equation. Okay? It will always show you the final last equation, which is not that easy to understand what's going on. Okay? So we start with this intuition. Make sure that you really get the idea where it comes from, and then we are going to spend the time doing the optimization.